I live alone, and for the past 3 weeks, I've kind of been by myself. And I tend to talk to myself when I'm by myself, and I've gotten so used to it that if you find me just rambling on to myself, that's because I forget that there's other people around. Okay? That's a joke. Unfortunately, I saved my lesson this morning, but I didn't save it, so it got lost somehow. So I'm just going to be working off of this PDF document. The first lesson is dealing with solving systems of equations graphically, which you already know how to do. So as a warm-up, we're going to solve this system of linear equations that you knew how to do in Math 10 graphically. And I want to spend some time explaining to you what this is actually about by talking about each of these equations separately. So let's take 3x minus 2y equals 12, and let's rearrange it for y. We're going to rearrange that equation for y because that's how we enter things into our graphing calculator. If we wanted to graph these on paper, we would still need to rearrange for y because that's how you can tell what the slope and the y-intercept is. So in order for us to rearrange this for y, the first thing you're going to probably do is move the 2y to the other side. Subtract the 12 from both sides. Hopefully, I know it's easy to forget stuff, but with math, hopefully you haven't forgotten over the past 3 weeks how to do this. If you have, then you're in real trouble. Now what I'm going to do is divide everything by 2, and I'm the kind of person that prefers to do it this way. I don't like just going over 2, the whole thing over 2. I'd rather put each piece over 2. And we end up with y equals 3/2 x minus 6. Okay, I want to talk about what this means. Well, let's put it in our graphing calculator. Y is equal to 3/2. I'm going to use some decimals here. 3 over 2 is 1.5. So 1.5x minus 6. See, and I think what happens, particularly in high school, is you get into the algebra, you get into the abstract, and you forget what this is all about. When I graph this, and let's go zoom standard, what does that line mean? I suspect most of you don't know how to answer that question. What is that line? I know it's y equals 1.5x minus 6, but what does it mean? What is it? How is a line an equation? How does that work?
You look for where y equals 0, and then that gives you value, I guess.
Well, as soon as we look at where y equals 0, then you're talking about a specific point on the line. I'm asking a more general question. What I'm asking is, let me do this a different way. I'm saying that this is a very difficult question I'm asking you to ponder, by the way, is the same as this. And I don't think this is something too many of your teachers have ever explained to you. How are they the same? I mean, this is a picture, this is a formula. Let me ask you a question. Is 1, 9 a point on this line? No. So what does that tell you about x equals 1 and y equals 9 in the equation? Boy, first day back after 3 weeks, and I'm asking you to really think hard about this. This is difficult. Seamus. Perfect. It means that if I put 1 in for x and 9 in for y, I'll get a false statement. In other words, 1 comma 9 is not on the line, and 1 comma 9 does not satisfy the equation. So what is a line? A line is an infinite number of points. There are an infinite number of ordered pairs on this line. And every one of those ordered pairs makes this equation true. So, for example, and I know this is nitpicking almost. It's like, wow, do we really need to know this? I'm going to say yes to understand what we're going to talk about here. If I were to go trace 2, since 2 comma negative 3 is a point on that line, that means in the equation, when x is 2, y is negative 3. Are you with me on that? So, how many solutions to this equation are there? An infinite number of solutions. An infinite number of ordered pairs make that equation true. Okay. Let's do the second equation, which is 5x plus 3y equals 39. Let's write this as y equals. And you know what? I suspect many of you could just write y equals right now and put what it's equal to. But I'm going to show a couple of steps. I'm going to move the 5x to the other side. And then I'm going to divide everything by 3. So what do we get? Negative 5/3 x plus, is my division correct? 13. So bear with me here. I want to try something different. New, yeah, sure. So I've got my first equation plotted on that calculator. I'm going to plot my second equation over here on the second calculator. Oh. Is it 5/3, negative 5/3 x plus 13? There are other ways I could have entered that, but that's how I've chosen to do it. And I'll go zoom 6. So, what does that tell you? That tells you that for the second equation, any point on this line is a solution to the second equation. Right? So, what does it mean to say, what's the solution to a system? It's asking you to find a number for x and a number for y that make each equation true for those same numbers. So, for example, didn't I say 2 comma negative 3 was a solution to this equation? Is it a solution to this equation? Well, it would be if it's a point on the line, wouldn't it? And to see if it's a point on the line, I could go to my calculator and go trace 2. No, not even close. So how do we find, this is how it was taught to you originally in grade 10. How do you find the numbers for x and y that make both equations true? They have to be the same numbers that are on each line. So they have to be where the lines intersect. Does that make sense? I mean, I think many of you would have just remembered that the solution to a system is where the lines intersect, but this is how come. This is why. So, there are an infinite number of pairs of numbers that make each of those two equations true, but there's only one point that makes them both true. And that's the point of intersection. And Anybody remember how to find that point of intersection? On your graphing calculator, what you do? Isaac?
You go to second trace.
Right. Second trace, you go into your calculate menu and, intersect. If you have only two different graphs, you don't need to overthink things. You hit enter, and as long as you can see the point of intersection, hit enter 3 times. First curve, second curve, decline the offer of guessing, and just hit enter. So 6, 3. I don't have my glasses on. Does that say 6, 3? All right, so the solution to the system is x equals 6, y equals 3. I'll tell you, I'm really not a big fan of just putting brackets 6, 3. I'd rather say x equals and y equals. You remember doing that last year? Would have been the very last unit in Math 10. You don't. It's been a whirlwind. Okay. Right. So, what we're going to be doing in this unit is we're going to continue to solve systems of equations, but the one we just solved had a linear equation and a linear equation. They're both linear equations because when we graph them, we get lines. We're going to be solving systems of equations that are called linear quadratic systems and quadratic systems. What does this mean? It means that if we solve a linear quadratic system, one of the equations will be linear and one will be quadratic. It means that if we solve a quadratic system, the two equations will each be quadratic. So, for example, just looking ahead, example 2 is a linear quadratic system of equations. Example 3 is a quadratic system of equations. So, some questions to warm us up though. The solution to a system of two equations, as we've just seen, is given by the x and y values, or the coordinates, of the point of intersection. Here's the first question. If you had a system of equations and one of the equations was linear and one was quadratic, how many different solutions to that system might there be? Keep in mind, the solution to the system is the point of intersection. So I would like everybody to ponder that. If you draw the graph of a quadratic function and you draw the graph of a linear function, my question to you is, how many different places could they intersect? Who's got an answer for me? Isaac?
They could intersect once.
Let's do this one at a time, though. Once? Okay. They could intersect once. That's true. What would that look like graphically? So we're saying there could be one solution, because Isaac is claiming that I can draw a quadratic function and a linear function, and they will only intersect once. How would I draw that? Well, I know a quadratic function is a parabola. I don't think it matters if it opens up or down. Let's open down. How would I draw a line now? So this is the quadratic one. How would I draw a line so that it only intersects once?
100% vertical.
Fair enough, but that is not a function. So I want to take a breather here and explain that. Definitely, any line, and don't draw this, any line that is vertical, if it's even off a bit, it's going to intersect somewhere else. Any line that is vertical would only intersect once. But the equation of such a line which you're not writing might be x equals 3. Because it's a vertical line, it's not a function. So, good thinking, but I should have stressed that it has to be a function. How can I draw a linear function so that it only intersects in one place?
If it's completely horizontal and it touches the parabola right at like the top of the ball.
Okay. That is true, but that's a very special case. So I want to draw this. What's being said is that this would be an example of a linear function which does that. And that is true. But is there another way to do it? I don't want anybody to walk away from this thinking it has to be that case.
Could it just like clip this?
Clip, I love that. It could just clip the parabola. And there's a word for that. Does anybody remember or know? When you have a line that just clips it, there's a special word for how that touches the line. Seamus, it looks like you maybe want to guess.
I know I've heard it, I just can't remember it.
The word is tangent. It has nothing to do with trigonometry directly, but it's tangent. So that would be one solution. Isaac, I'm going to stick with you because you had a whole list in your head, I think. What's a different number of solutions that it could have? Okay. And I hope it's clear what that would look like. Maybe the parabola looks like this, and the line looks like this. They don't intersect at all. Is there any other case? Could have two solutions. Excellent. I want you to notice, by the way, that this is really about the number of different solutions to a quadratic equation. And I don't want to get into the algebra of it, but if I give you a quadratic equation and I say, how many different solutions could there be? There could be one if the discriminant of the resulting equation is 0. There could be 0 if the discriminant is negative. There could be 2 if the discriminant is positive. It's not important, but I want to point out to you that there's a connection here between this and what we've already learned. That's it. They can't intersect 3 times, can they? Wouldn't think so. Possible. Okay. What about if the system of equations contains 2 quadratic equations? How many different solutions could there be? So while I am setting up some grids, you think about it. And I guess given that I'm drawing 3 grids, tells you that there's 3 different answers for sure. Let's start with 0. Is it possible that a quadratic system of equations can have no solutions? Well, if it is, then that means it's possible for 2 parabolas to never intersect. And there's lots of ways that can happen. Probably, let me make sure I wrote something here. I didn't really complete my thoughts here. 1 solution, no solutions, 2 solutions. Probably what comes to most people's minds here is if the 2 parabolas do not intersect, they probably look something like that. Is that fair to say? Is it possible, we can leave that up there. Is it possible to get no solutions if the parabolas both open up?
What if they were like the exact same and inside of each other?
Exact same and inside of each other. That would work. I'm not going to draw that, but what you're saying is if you have this parabola and you have this parabola, but one has been shifted up, every point is shifted up, they will never intersect. Is it possible? So yes. Is it possible for me to have the vertex of the second parabola here, but yet they never intersect? What if it's narrower? What if it's really narrow? Or I could have a parabola that's very wide down here. There's lots of ways you can get no solutions. Going back to this, is it possible to have one? Yeah, they just have to clip each other, right? There's lots of ways that could happen. This, let's take a wider parabola. Yeah, I mean, there's lots of places I could put it. I could put it there. I could put it here. This is what most people think of. They immediately think they have to be vertex to vertex, but they don't have to be. So one solution. Two? We're up for two? Sure. They just have to cross through each other. Maybe one of them is like this. Maybe one of them is like this. I know most people will automatically assume one has to be upside down and the other right side up, but it doesn't have to be. Two solutions. That is probably this parabola right here, one of the worst parabolas I've ever drawn. It doesn't look very symmetrical, does it? It's like it's being blown over in the wind, but you get the idea. Is there any other number of solutions? Well, there is, but it's not 3, and it's not 4, and it's not 5, and it's not 6. I can see that some of you thought you knew, and then as soon as I said that, you went, wait a minute. What's he talking about? Seamus again.
If they were the exact same, you could have infinite intersections.
Exactly. If they're exactly the same, which is pretty weird. That's excellent. But it's possible. It's possible to have, I'm going to use different colors here. Let's use orange for one of them. And let's use red for the other. If they happen to be, the word is coincident. These two parabolas are coincident. Then there are an infinite number of solutions. And that can't happen with a linear quadratic because linear and quadratic can't be the same. Okay, one quick question here before we get to the meat of this lesson. And this is example 3. The purpose of this example in my mind is to get you thinking about what intersections of functions can represent. A diver is training. She's diving from a 3-meter springboard, which means the springboard is 3 meters above the water. Her coach uses video analysis and plots her height above the water. So which of the systems could be representative of what's going on here? So we have two graphs there. One of the graphs is a parabola that opens downward, and that's going to be her height. So I think it's pretty clear that unless you're Wile E. Coyote, when you leave a springboard, you're not going to approach the water with that mathematical pattern. You're not going to just start falling at a regular speed. So this one is out. It's clearly got to be the ones that show her height. So she starts at this point and goes up, sploosh. Starts here, goes up, sploosh, etc. There's something about this question that's a little bit weird. There's not enough information given. But how many of you see that D is what we're going to go with here because it contains information about something else other than her height? What is that other line representing? Seamus, you're on a roll here. The height of the diving board, right? It stays the same the whole time. That's why this is out, because you see where she starts. It's not like, I don't know, hovers out half a meter above the diving board to the edge and then jumps somehow already being above the diving board. That's not going to happen. And this one is out because the diving board doesn't fall as well. So this is the one that contains the most information. Now, we're asked to analyze the important features of the graph. At this level, I probably would on an exam just say, here is the graph, tell me about the graph. So what are the important features of this graph? Give me a second. As I said, I didn't save my file. What are the important features of this graph? So first question is, what does the point of intersection of those two graphs tell you? I mean, it's where they intersect. Oh, Seamus, you're just... When she returns back to the height of the diving board. And hopefully the diving board, she doesn't jump off of the end of the diving board and go straight up. Because if she did, that point of intersection would be where she hits the diving board, right? She jumps off at an angle. So A is where she returns to a height of, we can actually be very specific here, 3 meters. There's another important point here, which I'm going to label as B, which is the y-intercept of the graph. So what does B represent? Let me make that a little bit more visible. What does point B represent? Somebody over here. Don't let Seamus take all the glory here. Come on, you guys. Seamus. No, Brody. Right, her initial height. The height of the diving board, her initial height. Lots of ways to put it. I'm just going to put initial height. But you could certainly write the height of the diving board. Somebody knocking at the door? No? Were you hearing a thumping? Oh, okay, good. That's good. Then it's not just me. What about point C? Reagan, what do you think point C represents? Right, it's splashdown time. Hits the water. There's one other point which I don't even think we need to write down, but I'll include it for completeness sake. D. point D, there's nothing important about these orders. Point D is simply the maximum height. You know, if you knew that point, you would know when she reaches the maximum height and what her maximum height is, which we already learned about and talked about extensively in other units. All right, let's get back to the kind of pure math aspect here. We've got 2 more examples to solve. Well, 3, 4, actually more than that. So let's take a look at example 2. Example 2 says solve this system of equations graphically. All right. Well, that means you need to rearrange both of those equations for y so that you can put them into your calculator to find the points of intersection. That's it. So I'd like everybody to rearrange the first equation for y. First equation being what I'm going to highlight in yellow. As soon as my computer catches up. It's a pretty easy equation to rearrange for y. Simply move the y to the right-hand side where you'll have x plus 1 left on the left-hand side, and you're done. Rearranging the second equation for y, which I'm going to highlight in green. Problems here. What's going on? All right. Also a pretty easy equation to rearrange for y. The y is by itself, if we can get rid of the x squared, the negative 6x and the 3. So let's just subtract those to the other side where they all switch signs. Are we in agreement on these 2 rearrangements? Nothing really taxing there. So now you have to put them into your calculator for y1 and y2 and find out where the points of intersection are. Zoom 6 is always the way to go. I made a mistake here. The mistake I made is I didn't check to see if I entered everything correctly before I hit graph. And I do think that's a mistake. And I didn't. By the way, I didn't know I didn't. I honestly didn't check. Jackpot. There we go. Oh. We even lucked out because the 2 points of intersection are very visible. Now, remember when I told you that you go to your calculate menu and choose intersect, I said just hit enter 3 times. The only thing to note here is that since there's 2 points, when I hit enter 3 times, it's going to find the point of intersection closest to wherever the cursor was. That's all. So 1, 2. And when I repeat the procedure, I choose intersect, I just want to scroll so that my cursor is closer to the next one. It's always going to look, I think what your calculator does is it starts looking in that vicinity and working its way out. And as soon as it finds one, it zeroes in on it. 4, 5. I don't think we need to check it. Verifying it is there. We've verified it. It's on the same, the point is on both lines. If you wanted to verify it, here's what you would have to do. Put 1 in for x here, and you'll have 1 plus 1. Put 2 in for y. You get a true statement. Put 1 in for x in the second equation. If you get 2, then 1 comma 2 is a solution to the system, and you will. Then you repeat it with 4 comma 5. Does anybody have any questions with how you would verify it if you wanted to? Okay. All right, piece of cake. Example 3. Solve this system. So you have to rearrange both of those equations for y. And quite frankly, I hope you're in agreement. Both of these equations being rearranged for y is very easy. The first equation will be y equals negative 2x squared. Boy, I better not screw this up after saying how easy it is. Minus 16x minus 26. The second equation rearranged for y would be y equals x squared plus 8x plus 19. Are we in agreement there? The first equation, I simply moved everything but the y to the other side. The second equation, I moved the y to the other side. Negative 2x squared minus 16x minus 26. X squared plus 8x plus 19. Double check everything. Zoom 6. Again, you can see the points of intersection. Negative 3 comma 4. And guess I'm going to have to move further to this side now. Negative 5 comma 4. Those are our two solutions. Any questions with example 3? Pretty straightforward, I think. Example 4. The difference of two positive numbers is 30. And then when the square of the smaller is added to 3 times itself, you get 138 more than the larger. We got to decipher that and put that into an equation. The nice thing about this, everybody, is since we're dealing with systems of equations, we don't come up with a single equation just with one variable. We can use 2 variables. So the difference between the numbers is 30. I don't want to get into an in-depth explanation of something right now, but I will tell you that I would avoid using x and y when you set up these word problems. I will explain how come in a minute. Okay? So I'm just using a and b. By the way, if a minus b is 30, a is the larger, isn't it? The bigger minus the smaller gives you 30. B is the smaller. So I know I've explained this to you before somewhere else, but when you write an English sentence in math, certain words are written with certain mathematical symbols. So the square of the smaller is added to three times itself. the result, and this is a very important word in math, the result is, didn't want to use that color. The result is means equals. $138 more than the larger. Sorry, I got to use the pink one. And I'll rewrite that so we don't have to endure the colors. The second equation is 3b plus b squared equals 138 plus a. Now I'm going to ask you an important question. You have to rearrange these for a variable so you can put them into your graphing calculator, right? You need to rearrange for y. What are you going to rearrange for? Are you going to rearrange for b or are you going to rearrange for a? A. Because you can't rearrange this equation for b, can you? Our quadratic equations are always y equals, and then there's x squared and x. And this is why I said don't choose x and y to begin with, because would you agree that you could have, please don't write this down, but somebody could read this question and say, well, x minus y equals 30, and 3y plus y squared equals 138 plus x. You could do that. But then you're looking at the second equation going, oh no, now what? Am I going to plot x on the vertical axis? It causes all kinds of problems. So we're going to plot these. The first equation is a minus b equals 30, which means I rearrange for a and get that. The second equation, I can rearrange for a by subtracting 138. And I would probably say to you that you know, everybody, how frustrating it can be to get the right zoom settings. This will be the point in time where many of you would much rather solve this question algebraically. And we will learn that tomorrow. Let me put these in. Y is equal to x plus 30 or 30 plus x. So first of all, that's a line with a y-intercept of 30. If I were to go zoom standard, I'm probably not even going to see that line. This is 10. It's way up here. That's where that line of x plus 30 is, which you should know, but we'll get back to that in a bit. And then I also want to enter and I need some help here. X squared plus 30x, no, plus 3x minus 138. I mean, I know the y-intercept of that quadratic function of that parabola is negative 138. It's going to be something that's not visible. Oh, something appeared there. I'm guessing that this parabola looks something like that. And I think my only real hope here, unless I want to complete the square and start looking at x-intercepts, is to go zoom out. I think this is our best hope. Make sure I entered that correctly. Yep. Zoom out. We don't often use it because it's not a very valuable thing. Oh, there's a line. Okay, we're getting somewhere. Oh, we're getting somewhere. I can't quite see that other point of intersection, so I'm going to increase my Y in the window setting to say 50. And the word I would describe to find the solutions graphically sometimes like this is clunky. It's clunky. It's not a very efficient, streamlined process. So let's see, intersect. Let's go to the right first. 12, 42. So what does this mean? It means the two numbers could be 12 and 42. I just want to pause for a second. You can use your calculator for this. Is the difference between these numbers 30? Good. If I take the square of the smaller and add it to 3 times the smaller, will I get 138 more than the larger? So if I take the square of the smaller, that's 144. I add 3 times the smaller. 144 plus 12 is 154. Is that, did I do that right? No, 3 times. There we go. So 12 squared plus 3 times 12 is 144 plus 36, which is 180. Okay. Is 180, 138 more than 42? Yes. Or negative 14 and 16. Do they have a difference of 30? Yes. 16 minus negative 14 is 30. And I won't go through the calculations, but if you square the smaller, negative 14, and you add 3 times the smaller, you will get 138 more than the larger. Is there anything in the question that said the numbers are positive? There is. 2 positive numbers. Oh, well, we didn't even need to waste our time with this. This is the answer. All right, one more quick question to do. How are you doing? I'm not overloading you today? Okay, good. The last question has to do with, and I'm giving you this question because you should know these words to do well in certain areas in math. The words are cost and revenue. Don't confuse revenue in business with profit. As a business person, revenue is any money that comes into my business. That's not profit. If all the money that came into my business were profit, I would be some kind of wizard because that would mean I'm running a business without any cost out of my pocket. So if I'm going to retire from teaching, I'm going to be a hot dog vendor in Sylvan Lake. I have to buy hot dogs, I have to buy buns, I have to get a permit, and then I sell the hot dogs. All that money comes out of my pocket, and then I take some money in. When the cost that the business person pays equals the revenue, the money they bring in, that's called the break-even point. If you're running a business for the first time, in the first year, you hope to break even. If your cost equals your revenue, that's break even. What would you call this? Think about that for a second. How would you describe a situation where the cost is smaller than the revenue? Actually, no, it's a profit. This is saying your revenue is more than your cost. This is saying this is my cost. Here is my cost. Here is my revenue. This is actually profit. And deficit or loss would be that. Okay, so what's the break-even point of this particular business? You've got a cost function. It says the cost to produce n items is that. If the function notation is bothering you, then just think of it as cost equals, okay? It's given with function notation because it's just telling you cost is a function of how many items you sell or produce. And it makes sense that if you're selling everything for $20 a pop, your revenue would be equal to 20n. And again, if the function notation bothers you, don't use it. So question A says, how many items do you have to sell to break even? Which means we have to solve this system of equations. You're going to put into your calculator y equals 20x and y equals 2500 plus 22 minus 0.15 times x times x. Watch those brackets. Double check to make sure you enter everything correctly. Now, I suspect that this is going to really be the place where some of you just kind of want to throw your hands up and go, show me how to solve it algebraically. I think. Because if I were to go graph, the likelihood that I'm going to see anything here is really small, particularly that we have this number of 2,500. But what I can do, and we've talked about this a little bit before, is I can go to my table feature of the calculator to kind of gauge where these might be getting close to each other. So I'm going to set up my table to start at 0 and go up by 5. I don't know what these items are, but let's look at multiples of 5. It's selling none and 5, etc. And make sure that you change it to automatic all down the line. So second graph gives me this. So check it out. I don't sell any items. Guess what? I lose $2,500 because I don't get any money in. These numbers are starting to get closer to each other. Y1 is my cost, Y2 is my revenue. And my revenue is slowly getting closer to my cost. We have an option here. We could continue to scroll down, or we could think a little more intelligently and change the table setup to start at like 100 and go up by, I don't know, 25. It's up to you. Oh, yeah, okay, there we go. It's negative. Oh, because I'm going in the wrong direction, I probably put, let's try that again, 100. There we go. So it's looking like somewhere around 125 to 150 items. They're kind of hovering close to each other. I shouldn't be so dismissive. I should take the time to explain this. At 125 items, the cost is bigger than the revenue. But at 150 items, the cost is smaller than the revenue. So it's somewhere between 125 and 150 items. That tells us we should be looking in our window settings up to about 150. It's going to intersect someplace in that domain of up to 150. How many of you might have just put 125 to 150? I think it's better to go to 0, but it doesn't really matter. Now, what are we going to put for Y? Well, look at your tables. Your Ys are hovering around 3,000. So I would say 3,200. This is one of the most frustrating things for me. I can find a good picture on my graph, but it's incredibly difficult to explain it to students how they can do it. If I had my choice, I would just solve this algebraically, but you don't know how yet. Yeah, there we go. And by the way, everybody, in case it's not clear, this is frustrating, isn't it? Trying to find the right window settings. It's not just you, it's everybody, including me. But now I can find them, the point of intersection, that is. I didn't even bother to scroll over there. So it intersects at 135.9 comma something. So this is a little bit awkward too. What's the break-even point? Is it 135 items? Well, at 135, you're not breaking even. Is it 136? Well, at 136, you're not breaking even. But if you were given this on an exam question, it would say round to the nearest item, and you would put 136. Okay? So that's what we're going to put here. The break-even point is 136 items. For what number will there be a profit, and for what number will there be a loss? Well, a loss is less than 136, because when we looked in our table less than 136, we had more cost than revenue, and your profit is selling more than 136. Yeah.
Wouldn't you have to put for the profit, you'd have to put a line under the greater than sign? You would be making profit then at 156.
Yes, but and that's because of that decimal, right?
Yeah.
Okay. Let's imagine, I keep going to adjust my glasses because everything's blurry and I'm not wearing them. Let's imagine that it was exactly 136. If it were exactly 136, do you agree that that what I've written here would be correct?
Yeah.
Okay. That's all we're doing. We're just saying if it were exactly 136. Otherwise, if we do what you said, then we can't really put n equals 136 here. So it's kind of a goofy question. Anyway, does that answer it, Seamus?
Yeah.
Okay. You know, the biggest part of today is solving systems of equations graphically and solving word problems as well. The profit loss, the springboard stuff, that's just kind of getting your brain warmed up. You can see what the practice problems are. I hope that was an okay return. Page 435, there's a few questions, and then there's additional problems on page 4 of the unit handout that I would like you to try. So you got about 20 minutes here, it looks like. Oh, no, you don't. Went longer than I thought. You've got about 15 minutes, but get started, try a few of these, and we'll go over them tomorrow.